So my talk is on multiplexer based on skyrmions confined by energy barriers in magnetic nanotrack. So the outline of this brief talk is like this. First, I will briefly explain about the magnetic skyrmions in a ferromagnet, and then I will give a brief introduction of my design of the device and the parameters which I use for the simulations. And then I will introduce the 2 to 1 multiplexer and 4 to 1 multiplexer based on skyrmions. Let me clarify. My work is purely based on simulations. I use micromagnetic simulator tool MuMax 3 for the simulations. And the concept of skyrmions in ferromagnet goes on a bilayer or on a trilayer AFM structure. Like in a bilayer ferromagnet and heavy metal structure, the skyrmions can be developed and by means of current or voltage. And here I consider the generation of skyrmions by using magnetic tunnel junctions on a ferromagnet layer. The skyrmions form at the interface of ferromagnet and heavy metal. Uh, so there are many type of interactions when we look into a ferromagnet. So they are exchange interaction and anisotropy and uh, the dipole interactions and other things. And when heavy metal and ferromagnet come together, we can see the Zarinsky-Muria interaction also. The exchange interaction always tries to keep the magnetic moments parallel or anti-parallel to each other. So if it is parallel type, then they will be all aligned in the same direction, and if anti-parallel, then they will be aligned in opposite directions. And so in case of ferromagnets, they are always parallel. And the Zarinsky-Muria interaction tries to keep the neighboring magnetic moments perpendicular to each other. So as a role play between these two interactions, the skyrmions form at the interface. So the skyrmions look something like this. They can't we can't call them parallel to each other or perpendicular to each other. So it forms a round kind of this topology with its center pointing in some direction and the periphery magnetic moments pointing in the opposite directions. And this topology is this topology always remains constant, always remains same. So if we try to manipulate it by by some external force, like I'm considering the use of current to move the skyrmions. So by the application of current, we can move this skyrmion from one end of the device to another end of the device. The skyrmion moves in the direction of current applied itself. And by the movement, it is like the magnetic movements are flipping their directions. It's not like some physical entity is moving. It's just that the current is flipping the magnetic movements in a preserved topology as it flows forward. So these magnetic skyrmions are visualized by they are visualized by many research groups. One of them reported this kind of skyrmions in a COPT bilayer film from Spintech. So these skyrmions are stable structures on a FM. Even at room temperatures, there have been many reports recently which confirm that skyrmions can be found at uh, room temperature as well. So this is the basic fundamental of my research work. And there was another report recently, another group who reported that the ferromagnet can be patterned in any desired in any desired track. Like we can design any track on a ferromagnet by using helium plus radiation. So the helium plus ion itself can change the material parameters of the ferromagnet layer. The helium plus ion can reduce the uniaxial anisotropy and the DMI coefficient of the particular region where it is irradiated. So uh, by this, uh, the skyrmions can be easily placed on the patterned track, and the unpatterned track or the non-irradiated part of the ferromagnet works as a barrier for the skyrmions. So the skyrmions can be okay. So these tracks can be created by helium plus ions, where the skyrmions can stay and they can move. Uh, and next. So this is my device. This is the 3D schematic of my device. It's a multiplexer. So here the SL is the select line and A and B are the inputs and Y out is the output. So from this equation, we can understand that if select line is 0, then output will be equal to A. And if select line is 1, then output will be equal to input B. And from this truth table, it is easily explainable. So if select line is 0, then output follows the input A. And if input is select line is 1, then output follows the input B. So here the input B is provided at uh, this position from the MTJ and by voltage VB, and voltage and input A is provided at this position by this MTJ TW1 by using voltage VA, and the same select line is given to two positions at these two places, and we collect the output at the other end of the device by using by using a read MTJ, and the current is applied in the x direction, and the skyrmions also move in the direction of the applied current. So the device dimensions are 512 nanometer in length and width. And this figure A shows the track design of my device. So this X0 track is for input A, X1 track is for select line, and X4 track accommodates input B and both and select line also. And this is the position where we collect the input, the output. And these are the simulation results for my 2:1 multiplexer. So this is the first case when select line is 0 and inputs are A and A equals to B and B equals to 0. So we expect that the output should follow the input A. So this is how the skyrmion moves. Since both select line skyrmions are 0 and input B is 0, so only input A is present, and this is the trajectory that is follows. And next is the case when select line is 0 and inputs are 0 and 1. So we anticipate that it should again follow the input A, and since input A is 0, so output should be B. So the output also should be 0. So this is the trajectory of the input skyrmions. It just enters and gets trapped, and we get 0 at the output. And then there is another case when select line is 0 and both inputs are 1. So again, we can anticipate that output should follow the input A. So if input A is 1, the output should be 1. So again, the Skyrmion follows this trajectory. It crosses the small opening from this track to this track and goes to the output. Okay. Okay, so similarly, these are the simulation results for select line equals to 1 cases. And here the select lines are first introduced, and later the input A and B are given. And this last case will explain it clearly. So select line and both inputs are 1 in this case. So first select lines are entered and then input A and B enters. So in this case, if select line is 1, then we anticipate that the output should follow the input B. So this input B Skyrmion follows this trajectory and appears at the output. So this way we achieve the multiplexer function. And we can also cascade the proposed multiplexer to design for the 4:4 to 1 multiplexer and the basic logic also like AND, NAND, OR, and NOR. So this one is the case for a 4:1 multiplexer. Okay. Okay, so our proposed 2:1 multiplexer consumes almost 20 femtojoule of the energy, which is quite low in terms of device design. So this is the energy consumption for Skyrmion nucleation detection and the transport also. And so this way we can
please conclude
use a
your
very small, like we can increase the device density on a chip itself, because so this was my time. Thank you so much for listening.
okay. Thanks for the talk.
If there are any questions, then I'm not able to hear anything from other end.
Yes. So there is no question part. Thanks.